Hi guys, let's start talking about chemical reactions. I'm going to minimize myself and then we'll go on from there. So chemical reactions, let's start. Chemical reactions signify and denote a chemical change. And a chemical change is when a substance is converted into one or more new substances. So this is caused by the rearrangement of the atoms. So the atoms in the reactants are rearranged to form some new product. This is recognized by new physical characteristics. So either a change in color, the formation of a solid, or the formation of bubbles as a change in the physical state, or heat is being produced or absorbed, meaning there's a change in the energy of the products. So these are just, again, the same things we just talked about, the types of evidence that we can look at. So knowing those types of evidence, let's apply them. Can you pick out and identify the evidence of a chemical reaction in the following? So for the first one, when methane gas in an outdoor heater burns with a blue flame, that would be the flame. Okay, so the gas, change in heat. If bleach removes a stain from a shirt, in this case, it's a color change. There once was a stain and now it's gone. Presto, it was a color change. The bleach actually removed and it came into a reaction with the molecule of the stain and formed a new product. Now, bubbles of carbon dioxide are released when baking soda is mixed with vinegar. In this case, it's the formation of a gas, the bubbles of CO2. And there they are all in red if you are following along with the PowerPoints. So again, chemical reactions include a rearrangement of the atoms, and they produce one or more new substances, and they have the appearance of new physical properties, hence either the gas, the solid formation, or the change in heat, or a change in color. Now, all chemical reactions we write as a chemical equation. And in order to do this, when we write chemical equations, we have our reactants on the left side. They come first. We then have an arrow designating the direction of the reaction. And then we have the products listed on the right side. Any of the lovely little subscripts that you see in parentheses, in this case, if they are an S, L, G, or AQ, means the physical state of the actual reactant or product, whether it's solid, liquid, gas, or aqueous, so in a solution of water. Anytime we see this lovely symbol called delta or a triangle over the arrow, that means heat is used to start the reaction. So here is a chemical equation. This is the combustion of methane. So methane can burn in the presence of oxygen and form carbon dioxide and water. The big thing is that we have to make sure everything is balanced. So in this world, because it's just a rearrangement of atoms, I should say, and everything that you have in the reactants is going to rearrange itself to form products. That means everything that you have in the reactant side, the total number of atoms in the reactants, has to equal the total number of atoms that are in the products. Because what you have is what you finished with. We're just rearranging them. We're not adding anything in. So in this case, if we look at forming water from hydrogen and oxygen, in this case, we have 4 molecules of hydrogen on this side, 2 of oxygen on the reactants, and we form 2 water molecules. Again, these are completely different, but if you were to count the number of atoms in the products and the number of atoms in the reactants, you see that they're equal. They're just rearranged and bonded differently. So we are going to balance some chemical equations. And there are some rules about when we balance chemical equations. And the first thing, and the major one, is that if there are any subscripts, say right down here, Al2S3, those are never changed. We can never change subscript numbers. The only thing we can do is change the whole number coefficients that come in front. Now those whole number coefficients are placed in front so we can balance. And these means these are the number of molecules we have needed to balance the equation. So if I know that I am going to form Al2S3 and I only have aluminum and sulfur here, that means that I am going to need at least 2 aluminums on the reactant side. So that's where the 2 comes in for the coefficient. I'll also need 3 sulfurs on the reactant side, and there's where that coefficient of 3 comes in. So I'm just changing these whole numbers that are out in front. And they have to be whole numbers. You can never have half of an atom, okay? All or nothing, so only whole numbers. When we balance chemical equations, the way we do this is we make a lovely little list. And we're going to look and compare the atoms of each in the reactants versus the products. So again, this is the combustion of methane. And here, this is a balanced reaction, but we're just going to double check that it's balanced. It says that 1 molecule of CH4 or methane will join up with 2 oxygens, but they're double, so dioxygens, okay, to form carbon dioxide and 2 water molecules, H2O. If I look at all of the atoms here, I know that there's 1 carbon, that there are 4 hydrogens, and I have 2 times 2, so I have 4 oxygens on the reactant side. If I now look at what's on the product side, I have 1 carbon, and here I have 4 hydrogens, because 2 times 2. And if I'm counting with what I have on the atoms of oxygen on my product side, here I would have 2 plus, in this case, this isn't just 1, but it's 2. Okay, so 2 times 1 are 2. So 2 plus 2 gives me 4. Because all of these numbers add up, we're completely balanced and we're good. There will be instances where we have to actually balance the chemical equation. And in this case, the big thing that you have to do is you have to write the equation using the correct formulas for the reactants and the products. Make sure everything is above board and looks good to start with. Then you're going to count the number of atoms in each of the elements, okay, in the reactants and products. You're going to make your chart. Then we're going to use coefficients to balance each one. And then we'll just double check to make sure we're good. So if we are looking, and the same thing works, that we can balance any equation. It could be a polyatomic one, it could be a combustion reaction. It doesn't matter as long as everything on the reactant side equals everything on the product side. When we go with polyatomic ions, just remember, just like when we were doing them in ionic compounds, they travel together and stay together. So we balance them as a unit. So let's take this reaction here and see if it's balanced or not. In this case, I am going to go through as it is. And we're making a list of reactants versus products. I want to know how many sodium atoms I have. That's 2 times 3, so that means I have 6. On this case, I have 2 PO4s, that's a phosphate group. Here I have 3 magnesiums and 6 chlorides. And then you can go the same and do the products. We have 1 sodium, 2 PO4s, 3 Mgs, and only 1 Cl. So technically, our phosphates and our magnesiums are balanced, but our sodiums and our chlorides are not. So we really need to change what we're doing here. And how do we get, if we're looking at this reaction, how do we change these so the amount of sodiums and the amount of chlorides will balance? Well, we know what we have. We're going to have to use whole number coefficients. So I'm going to switch over my video to the document camera. And I'm going to make it bigger now. I'm going to try to make it bigger. So hopefully we can see what's going on. So if I have, remember I have a 2 Na3, and I'm just going to put this in parentheses to make it easier, PO4 plus, and I have a 3 MgCl2. And it's going to make, remember we're going to have a coefficient here. It gave me my 1 Mg3 PO4 2 plus some amount of NaCl. What do I have to do to balance all of this? I'm sorry, this looks a little out of focus. Hopefully it's a little bit better. In order to balance this, the only thing we have to do is we have to get back to making sure that we have 6 sodiums and 6 chlorides. Well, hey, look over here. I just have to put a whole number in front of it. And the whole number, because these are 1 to 1, means I just put the number 6. And we are completely balanced, okay? So that's what we mean by just using those whole numbers. So you write it down, you see what's there, and then you balance them off. We're going to do one other one just to double check and make sure how we're doing. So the one I would like to do with you is looking at the combustion of glucose. That's always a good example. So in this case, I'm going to have, we're going to do C6H12O6. Oops, sorry, my 6 went up really high. Oh, this is glucose, okay? Plus some amount of O2 is going to give me some amount of carbon dioxide and some amount of water, H2O, and then energy. Can't forget the energy when you break your food up. So if I make myself a list, C, H, and O, that's all we're using. And I have my reactants and my products here. Currently what I have is I have 6 carbons, 12 oxygens, and now I have 6 plus 2, I have 8 oxygens. On this side, I have 1 carbon, I have 2 hydrogens, and I actually have 3 oxygens, 2 plus 1. So we're definitely not balanced. So let's start with balancing carbons first. I have to get this equal to 6, meaning that I'm going to multiply this by the whole number coefficient of 6. So now that changes the amount I have in my products. It also changes the amount of oxygens I have. So now I have 6 times 2, which is 12, plus 1, can't forget about that. So now I have 13. So let's keep going down the line because we're working with balancing starting off of this molecule here. I have 12 hydrogens. So what do I need to do to get 12 on this side? Every time each molecule of this has 2. So I'm going to take 12, divide it by 2, that gives me 6. That goes there. So now my hydrogens are balanced at 12, but because I now have 6 here, it changed my total number of oxygens. So I'm no longer 13. In this case, I am 6 times 2, so I'm 12 plus 6. That gives me 18 total oxygens. Well, right now we're balanced in carbon, we're balanced in hydrogen, but 8 and 18 are vastly different. So what do we have to do here? We have to note that there's 2 different places for oxygen, right? So if we're balancing this one first, going through this, we have to remove the 6 that are associated with this glucose molecule. So I'm just going to take that 18, I'm going to subtract 6 away, that's going to give me 12. So now I have to have 12 oxygens accounted for in this molecule. Well, 12 divided by 2 gives you 6. So I have my 1 out in front. So now if I know and I double check my oxygens here, I have 6 plus 12, I now have 18, and we're completely balanced. So I just want you to feel comfortable going through and trying to balance some of these chemical reactions, okay? So the last thing we're going to talk about are just types of reactions. There are 5 types of main reactions that you will see. And almost everything can be divided into those 5 reactions. So as we're going, the 5 of those are, the first one is combination. That's when 2 elements become 1. So we can kind of think of it as A plus B is going to yield me AB. They combine together. The second one, a decomposition, is basically just the reverse of a combination. It's when something, say AB, breaks down to form its normal elements. So one breaks down into two. Then we have our cool replacement reactions. These we really see a lot when we talk about organic chemistry too, but they involve in realistically ionic bonds. So we're going to talk about single replacement and double replacement reactions. So in a single replacement, I have one thing, element A, is going to replace an ion, okay, of the first. So usually it's the cations, the positive ones that are switching. So A is going to replace and switch places with B. So it's going to yield me, in this case, B plus AC. They just switch places, nothing more. And a good example of this would be if you're getting stuck. Say I had zinc plus HCl. The zinc and the hydrogen are what's going to switch places. And that is going to yield me, in this case, zinc chloride and hydrogen gas, which would be H2. This isn't balanced, but this is basically what's happening. Hydrogen is switching with chloride. Okay. And a double replacement is a cation switch. These ones are fun. So in this case, it's the two positive ions that are completely going to switch. So A and C, the two positive ions, the ones that come first, the metals, are going to switch places. So what you're left with is Cb plus AD. Okay. That's a double replacement when two things are switching places, okay? Because I have an element where I have two, double replacement. And the last reaction is a combustion. So in any combustion, what you have to know is we have some form of what we call a hydrocarbon. The X and Y just means that these could be any ratios of numbers down here. This could be C2H8. It doesn't matter, okay? They're just certain numbers. So it's going to be some carbon compound. I'm going to have oxygen add to it, and it is going to combust and burn and break down into carbon dioxide, water, and some form of energy. And anytime you see energy, it could be in the form of like kilojoules or calories or something like that. So whenever we see a carbon-based compound in the presence of oxygen and it breaks down and the products are carbon dioxide and water, it's always combustion. So again, here they are. This is combination, two becoming one, like the formation of magnesium oxide. Decomposition, when one thing breaks down into two. So if we think of the decomposition of mercury oxide breaking down back to mercury and oxygen. Single replacement, one is replacing the other, okay? So this again, so we talked about with zinc and HCl. If you add zinc to hydrochloric acid, what's pretty neat is the zinc will basically look like it dissolves. So it becomes zinc chloride, and then you see all this bubbling, and what's happening is hydrogen gas is being released. So it's pretty neat. In a double replacement, this is a cation switch. The two positive ions are exchanging places. So in this one, Ag and Na are going to switch spots. So instead of silver nitrate and sodium chloride, I'm going to result in silver chloride and sodium nitrate. So those are a double replacement reaction. And then a combustion is any carbon-containing compound given, well, adding in oxygen and then producing carbon dioxide and water and some form of energy, okay? So this would be the combustion of methane as an example of that. So you need to know these 5 reactions And being given something that looks like this, an example, I want you to be able to classify that reaction. So you'll be asked to do that on a quiz and probably on an exam as well. So if we go through this learning check as a good example, the first one, 2 becoming 1, this would be combination. The second one, I have mercury is switching places with hydrogen. So this is a single replacement. In number 3, we're going to see lead and our potassium switch. So this becomes a double replacement. In 4, I have one thing breaking down into 2. The breakdown is a decomposition reaction. And the last one is a combustion because I'm forming carbon dioxide and water and energy. So there they are for you. The other type of reaction when we think about it is anytime we form an ionic compound, we actually undergo this. It's called oxidation reduction, and we also do this in biological molecules. It is how we oxidize a lot of our food and actually end up producing energy. This is realistically stage 3 of metabolism. So in all redox reactions, electrons are transferred from one substance to another. Sounds familiar? And we've already talked a lot about this, believe it or not, and did the prep work when we started talking about forming ions and ionic bonds. Because an ionic bond is when one completely transfers its electrons to another. So you've already seen and done a little bit of oxidation reduction already without even knowing it. So it's not as scary as it seems. But we also see this in the electrical energy of batteries, iron rusting, and again, our metabolism. It is stage 3 of metabolism. So here's the big thing that you need to memorize and just get in there. And if you get this acronym, you're good. But oxidation is a loss, reduction is a gain. So think of oil rig whenever you think of redox reactions, okay? Oxidation is a loss of electrons. That means anything that is being oxidized is going to become more positive, and it's going to lose its electrons. The electrons will be shown in the product side because they are lost. Reduction is a gain. In a reduction, you are gaining electrons. You are becoming more negative, okay? And here we go. Here's our copper. I'm going from a positive charge to neutral. It means I gained. And in reduction, the electrons are in the reactant side. So RR, reduction is a gain. Okay? Oil rig. So if we look at it here, here is element A. It has an electron. It's going to transfer it to element B. When it transfers the electron over, element A is being oxidized because element A becomes more positive. Now, element B, since it gained the electron, element B is reduced. It became more negative. So if it helps you kind of think of a slide of a scale, sliding scale, anytime we go from negative to neutral or neutral to positive, and we're moving in the right direction, it is being oxidized. Anytime we go from positive to neutral or neutral to negative, and we're going in the left direction, and when we talk about this scale, we are going under reduction. So when we look at the formation of these ionic compounds, they are going through an oxidation reduction. In this case, all of the metals are being oxidized because they are becoming positive. If you become a positive cation, you are being oxidized. All of the nonmetals are being reduced because they are becoming a negative anion. So in this case, if I'm looking at what's happening between calcium, I'm adding solid calcium and solid sulfur, and it's becoming calcium sulfide together. Calcium in its solid state by itself is neutral. So when it becomes in its ionic state, it transfers its electrons. It actually gives them away. It becomes positive. It undergoes oxidation. Sulfur is going to gain electrons. So in its pure state by itself, it is neutral, but in its ionic state, it's going to become a -2. So because of that, it gained is being reduced. And again, the overall product, CAS, remember, is still neutral because -2 and a +2 cancel out each other. It's charge balanced. So, but one is oxidized, one is reduced. Same thing here if we were adding zinc to copper sulfate. What ends up happening is that the zinc is going to be oxidized, copper is going to be reduced, and what's pretty neat is there will actually, the copper particles are going to come out of solution and replace the zinc particles. So you'll see you'll end up actually forming copper. This is how we actually do electroplating. If you think of things that are like gold plated and things of that nature, or silver plated. We're using these chemical principles here. So again, the copper ion in solution is going to basically bond in, take on the electrons from a zinc. Okay, so the zinc ion is now going to be free in solution, and the copper is going to replace it, okay, as copper solid. So I want you to be able to tell me whether these are being oxidized or reduced. And you have to remember oil rig and where that electron is. And if you can do these, you're probably doing pretty good and you'll be in good shape for the exam. So if I take tin and it becomes from neutral to positive, my electrons are in the product side. This is being oxidized. If I took my iron and I became what we call more negative, I added an electron in and I went from a +3 to a +2, so I actually became negative. This is a reduction. If I looked at chlorine and I added 2 electrons to it and went from neutral to negative, again, this is a gain in electrons. The electrons are on the reactant side, so this is reduction. So oxidation, reduction, reduction. If we think about what's happening in what we call light-sensitive or transition lenses, these are actually pretty neat. So it's using the principles of silver chloride. It's how you get that mirror finish that appears to actually keep out the UV light. What ends up happening is the UV light stimulates an oxidation-reduction reaction. So we have just the ions by themselves. So I have Ag and I have Cl minus, and eventually they become themselves, the neutral versions. So we want to know which one is being oxidized, which one is being reduced. And this might be hard just looking at to say, I don't know, but remember we have to think of where the charge is going. So in this case, let's take it piece by piece. I'm going from positive to neutral. How do you get from positive to neutral? Well, you have to take a positive away, which means you are gaining in a negative, okay? So I have to add a negative in here to get to neutral. So technically, what it looks like is Ag plus an electron will give me Ag neutral. On the other hand, if I am a negative and I'm becoming neutral, how do I get rid of this negative charge? I have to give that electron away. That means if I were to clearly draw it out, I'd have to include that electron over here. Oops, sorry. In the product side. So now if I'm giving away an electron, this is being oxidized. If I am gaining an electron, I am being reduced. Okay, so they are there for you. Oxidized, reduced. Now in biological systems, sometimes we can instead of just having the gain or loss of an electron, we may also involve, in this case, oxidation, the loss of a hydrogen or the gain of an oxygen. And reduction may be the opposite of that, because reduction is always the opposite of oxidation, so a gain of hydrogen or a loss of oxygen. And when I say loss of oxygen or gain of oxygen, it just means the number of bonds to an oxygen molecule, or an atom, I should say. So here's a good example when we're looking at our biological coenzyme FAD, FAD. In this case, if I have a molecule here, some carbon-containing compound, it has 2 hydrogens, I'm going to give away those 2 hydrogens to FAD. And FAD is going to be reduced, it's going to gain them and become FADH2. In the process, what I don't show you here is that we actually form a double bond between 2 carbons, so those hydrogens just freely go. And now, because this lost 2 hydrogens, this biological molecule has been oxidized in the process. But we will get further into that later in the semester. So just understand this, okay? It always involves a loss or a gain of electrons, but it may involve either adding or gaining oxygens or hydrogens, depending on whether we're in oxidation or reduction. So now that we know the different types of reactions, we have to kind of get into the basics of how reactions occur, and this goes way back into some physical chemistry called collision theory. And this is how we get what we consider enough energy to overcome our activation energy to actually have a reaction occur. So 3 things must happen in order for that reaction to occur and reactants to go to products. One is that the reactants must collide, okay? They must physically collide in space. Now they also have to be oriented properly. Okay, so think of like a lock and a key with an enzyme. If they don't hit just the right area, nothing's going to happen. And the third and final part is that there must be a hit and collide hard enough that that collision energy is going to be greater than the activation energy. So the energy required to turn reactants into products is our activation energy, and the collision must provide enough oomph and enough power to overcome that hump, as we call it. If we think about activation energy or energy of activation, this is just the amount of energy required to break bonds in the reactants and form new bonds in the products. Now, if the collision energy is less than the activation energy, the molecules just fall apart and they revert back to reactants. If the collision energy is greater than the activation energy, the reaction actually occurs and we form products. We overcome what we call this transitional state. So it's just showing you they have to collide, they have to be oriented properly, and then there has to be enough energy in that collision for them to stick. Now this can kind of look complicated and there's more information than you actually need in here, but we're just hitting up on the basic principles here. That I have my reactants. This is just free energy or the amount of energy, and it's increasing, and this is just over time. So my reactants in space, A plus B, they have a certain amount of energy to begin with, okay? They're going to collide in space, hopefully. Now what we have here is we have a transition state when they're all connected. Now this transition state is basically once they're all collided, A plus B plus C. So I have all my reactants connected together. This is what we call almost like the collision state, the transition state, when they're all connected together. Now this is a high energy state, and this is what we consider to be activation energy. We need enough energy in this collision to overcome this high energy transition state. It doesn't like being in this transition state. So if there's not enough energy in the collision, it reverts back to reactants. If there is enough energy in that collision, it pushes past this transition state and forms products. Now, in this case here, because this activation energy can be so huge and require so much, it might take a long time for reactants to form products. We actually use enzymes in our bodies, and that's what this little other red line here is. An enzyme, and this is kind of going more than we need to, lowers the activation energy overall. So it means that reactions are going to occur faster and usually quicker. And it gives an alternative pathway for this transition state. That's how it lowers the energy required. Okay? But we'll get into that in enzymes. The big thing is if you remember that there were the energy of reactants and the energy of products, we can actually classify our reactions as either endothermic or exothermic. And we can do this with all reactions. So if the energy of the reactants are low and the energy of the products are high, this means that heat or energy must be absorbed in, okay, to form new products. And anytime we absorb heat in, we're becoming cooler. These are endothermic reactions. And our endothermic reactions will have a certain delta H that we'll look at, okay? We're gonna have products minus reactants. Endothermics usually end up having a positive. So as we're going through, we have exothermic. In this case, in our exothermic reactions, the energy of the reactants is greater than the energy of the products, so heat is released. And in this case, endothermic, heat is gained or pulled in. The energy is pulled in. So exothermic reactions, heat is released. It's going to actually have a negative delta H. And in our endothermic reactions, heat is absorbed. It will have a positive delta H. If heat is being absorbed, you're going to see it in the reactant side. If heat is being released, you'll see it in the product side. So I'm going to have an idea about these to be able to tell me and classify whether something is endothermic or exothermic. And to give you an example, here are three. In this case here, heat is being released. It is in the product side, so this is exothermic. For number two, heat is being what we call absorbed or taken in. It is in the reactant side. This would be endothermic. And going back to number three, this would be exothermic.